the screen visible?
Yes, sir.
Okay. So far, we have understood that if you are provided with any Boolean expression, you should be able to design a CMOS circuit. Basic structure is there will be a CMOS network. So there will be a CMOS network at the top, the NMOS network at the bottom. The CMOS network is connected with the biasing potential, which is also termed as the pull-up network, whereas the NMOS network is connected to ground, also termed as the pull-down network. Biasing potential is a positive voltage for plus VDD. You provide the same steps of input within the PMOS and the NMOS network. In other words, for particular input, the PMOS and the NMOS corresponding PMOS and NMOS transistors must be terminals must be shorted. We receive the output from the intermediate node between the PMOS network and the NMOS network. This is the basic pattern of the. Now, if you just cross-check regarding what is the Boolean expression you are realizing, so there can be two kinds of Boolean expression in two forms below the inversion bar, mind you. So if you are provided with a non-inverted expression, you need to convert that into an inverted form. And then within that inversion form, the expression can be either in a sum of product form or in a product of sum form. So there can be an expression called Z1 such that Z1 equals to A plus B C bar to B plus C bar. So this is basically a product of sum form using here. So what we find within the NMOS network, forget about the PMOS network. So say we are using a black box for the PMOS network, but our expression directly corresponds with the designed NMOS network. So we will be designing the NMOS network. So what will be the NMOS network in this particular case? It will comprise of 3 branches cascaded within each cascade form. So E plus C1. And from here you take the output Z1. So what is Z1? Z1 equals to A plus B C bar E plus C bar. So ultimately what we realize within the NMOS network is within a particular branch there is ordering of logic. So there is ordering of logic. Then there are 2 ordering of logic. One Boolean expression is just one Boolean variable is just without ORing off with any other Boolean variable. So that is debug. But the other two branches are ORing of logic. So these OR branches are ANDed, and at the output we receive the inversion of that. So in other words, first OR operation takes place within the NMOS circuit. So OR, then AND operation takes place. First the OR operation takes place, then AND operation takes place, and then invert happens. So this kind of logic gates are termed as OR and invert gates. So which is the logic gate? Logic gate is the whole circuit. So by the term gate, here we are referring to the whole circuit. So this is a OR and invert gate. So CMOS circuit based on below the inversion bar, whether it is a sum of product or product of sum. So this is a product of sum below the inversion bar. Product of sum below the inversion bar. So based on this, CMOS circuit can again be subclassified into AND or invert gate or an invert gate. So CMOS circuit can be broadly subclassified into OR and invert gate and or invert gate. So OR and invert, how it looks like we have shown. Now coming to the AND or invert. So if you are having a Boolean expression Z2, such that it is A plus B bar plus DEA. If this is the expression. So this refers to sum of product form. It's a P form. And what will be the structure of the CMOS circuit? Forget about what is the CMOS network, that is just the reversely aligned transistor. We'll be using that as a black box. And here, it is A plus BC plus A plus reversible plus DEA. So there are three parallel branches. A reversible D, E, and F. Now you ground this, take the output from here. That is Z2. What is Z2? It is A plus reversible plus DEA. So within a particular branch, first ending is done. Here there is no ending when there is a single variable in a branch. But the other branches, ending is done first, and then these three branches are OR, and then the inverted logic you receive as Z2. So this is ending is first is done, then OR logic, and then invert. So AOI gate. So what is the AOI gate? Now this gate is not just the NMOS network, rather the whole circuit is nothing but the AND or invert gate. Is it clear? Now, you may ask me, there can be an expression, let's see, which once minimized or rather gives you an expression A plus B into C plus DE plus invert divert. If this is an expression, then what is the form? So ultimately, we will consider the broad sense of the form. Here, ultimately, there are sum of products happening. So maybe within the first form, it is something of a product of sum, but the whole expression is giving a sum of product form. So what is the whole expression giving? What kind of form below the inversion bar? That kind of gate it is representing. So as because the whole expression is giving a sum of product form, here it will be, of course, AND or invert gate. Here it will be represented by an AND or invert gate CMOS circuit. So the CMOS circuit representing or realizing this expression must be an AND or invert. Am I clear? Students, is it clear? Yes? Any confusion? Tell me. So we have used the example of two circuits, one for Z1 expression, another for Z2 expression, to further classify CMOS circuits. So CMOS circuits can be broadly classified into OR and invert gate and AND or invert gate. So based on what is the logic being realized within the NMOS network. So the logic being realized within the NMOS network is nothing but the Boolean expression form. So if the Boolean expression form is in a product of some form, then it will be a or an invert gate, OAI gate. Otherwise, if it is in a sum of product form, which is Z2, then it will be AND or invert gate. So here, which alphabet you will be abbreviating first depends on which is the innermost logic. So the innermost logic means the within the branches, within each of the branches of the NMOS circuit, within each of the branches of the NMOS circuit, what logic you are ultimately representing, that will come first. So ending is there within each branches of the NMOS circuit. So and or invert, because or means there are parallel branch. Inversion always comes at the last because the output is always found to be inverted, because you are realizing the logic below the inversion mark. So you will get the inverted output. This is because of the fact that the most basic kind of CMOS logic is extracted from the concept of a CMOS inverter. So inversion is the inherent logic demonstration of CMOS circuit. So any expression you realize within your NMOS network gets inverted and then the output is found. Now, if there is a mixture of QoS and SOC logic, then we need to find that what is the overall logic below the inversion logic. The overall logic is in a SOC form. Then the realized circuit, we term it as a AND or invert gate. If the overall logic is in a QoS form, then we term it as the or an invert gate, even though there may be inner logics of other forms. So, for example, there is an expression of Z force. There is an expression of Z force, which is uh, uh, or maybe X. So what will be the NMOS circuit? NMOS network. Then for the NMOS network, we have the pivot plus pivot. Pivot, pivot, yes. And so the Z force equals AB pivot plus pivot into X. So of course, it comes in a product of some form. So this is a product of some form. So this logic gate is nothing but or and invert or and invert. What is the expression that means Z5 would have been like this AB plus invert invert plus EA. Sorry, into E plus A. Then so this expression is a sum of product. This expression is a sum of product. But what is the overall expression? It is a the sum of product or product of sum.
Sir, the earlier is POS and the below one is SOP.
SOP.
Yes, correct. Earlier is POS. You consider
POS.
E also, right? Considering E also. So that is POS. And the overall is SOP. The duty is within this, if you consider only this, you consider only this expression, then
SOP.
again SOP. Right. So there are different formations of Boolean logic within different parts of the subsurface within NMOS network. But what is the overall logic realized below the inversion path? That is SOP. So if it is SOP, that is AOI.
AOI.
The whole, whenever we are referring that what is the logic gate of that type, we will be in the context of the whole expression below the inversion. But even though in between parts of the expression can be in SOP or QoS form individually. So if you are given any Boolean expression, you can either draw the circuit or you cannot draw the circuit. You can directly use your logic to tell that what kind of gate is that. Is it clear? Any confusion, anyone? Yes, is there any confusion? You can speak out. If there is any confusion, you can speak out. Or if is it understood? Yes, student. Is it understood up to this?
Yes, sir.
So broadly classifying CMOS circuits, it can be either in two forms, or an invert gate or AND on invert gate. So now we will study another variation of CMOS circuit, which is also a CMOS circuit, but it has a different name called pseudo NMOS circuit. What is a pseudo NMOS circuit? It is somewhat looking like a NMOS circuit, but that is practically a CMOS circuit. For example, there will be a load transistor. So the PMOS network is replaced by a load transistor, which is a PMOS transistor whose gate terminal is directly grounded. So gate is always having a 0 volt potential. The biasing potential here is positive. And then comes the NMOS network, which will be based on your Boolean expression, as we have done in all of our circuits. And this is the output. So here it is the input, NMOS circuit or NMOS network, grounded. So pseudo NMOS circuit looks like this. Why pseudo NMOS? Because it is just like a ordinary NMOS circuit, because here we are not using a PMOS network, but the load transistor here is a PMOS load transistor rather than a NMOS diffused N channel MOS transistor. So for NMOS circuits, we had a diffused N channel load transistor. We had a diffused N channel load transistor connected in that pattern for NMOS circuit, and here we have the NMOS network. Here we have the NMOS network with particular inputs, which was NMOS network was grounded, and we received the output. So this was the NMOS circuit which we had discussed in one of our lectures. This is NMOS circuit. Whereas this is not only comprise of the NMOS network but also PMOS load transistor. So this is the PMOS load, PMOS load transistor. So again, the concept of load transistor crops up over here, as because we have replaced the PMOS network or a pull-up network, and we have used this PMOS load transistor, the single transistor, whose gate is grounded. This gate is grounded. So how can we design this pseudo inverse circuit? Okay, so let us try to understand how we can design a pseudo inverse circuit. So for so what is this? What is this circuit, student?
Not gate.
Is that this is a pseudo inverse not gate. Similarly, this is pseudo inverse NAND gate. Similarly, we can have the pseudo inverse two input NOR gate. So if you are given an expression Z equals to AB bar plus A bar B, how to design the pseudo inverse circuit? So this is nothing but XOR, two input XOR. So the same technique. We have to convert that into a inverted form. So this is the convert. I have jumped the step. This is a conversion into an inverted form for the XOR gate, and you realize this expression below the inversion bar. So nothing but just realize this below the inversion bar. So CBT, this is Z, Z. Is it clear? Yes, students, is it clear? So design criteria for pseudo inverse pseudo NMOS circuit. So design the NMOS network as find the Boolean expression below the inversion bar. There shall be a single CMOS transistor whose gate terminal is grounded and source connected to the biasing potential. Potential that is large GDP. These CMOS transistor is the load transistor of the circuit and take the output from an intermediate node between the NMOS network and load. Is it clear? Yes, students? Please respond.
Yes, sir.
So, pseudo NMOS circuits are nothing but it's quite similar to NMOS circuits except the type of the load transistor. Here the load transistor is not a diffuse n-channel load transistor, rather it is a PMOS transistor whose gate terminal is constantly grounded. The NMOS network design criteria is same, which we have used for PMOS circuits or NMOS circuits or anything. So, just you need the Boolean expression to be converted into an inverted form so that the expression you get below the inversion bar may be realized within the NMOS network. The whole thing is done. The rest of the thing is connect the load as it is and the polarities of biasing potential ground and then take from the suitable point the output. So this is nothing but the design criteria. So why we needed pseudo NMOS circuit? So what is the
Sir, can you please show the point number 3, the last slide?
take the output from an intermediate node in between the NMOS network and the load. Is it clear?
Yes, sir, clear.
Okay. So let us now move to a very broad comparison between the circuits which we have designed. So we have started with the CMOS circuit. Then we have moved to NMOS circuit. Next, CMOS circuit. And now pseudo NMOS circuit. So the parameters, let us just jot down few parameters. Type of transistor. So type of transistor for CMOS circuit, it is CMOS transistor. For NMOS circuit, it is NMOS transistor. For CMOS circuit, it is CMOS and NMOS transistor. Pseudo NMOS circuit also CMOS and NMOS transistor. Then number of transistors, very important. Number of transistors, if the input is N, if input is capital N, then here the number of transistors are N plus 1. For NMOS, it is also N plus 1. For CMOS circuit, it's 2 into N. For pseudo NMOS circuit, again it is N plus 1. Then comes the biasing potential. Biasing potential. So here for CMOS circuit, it is minus VDD. For NMOS circuit, it is plus VDD. For CMOS circuit, it is again plus VDD. For pseudo NMOS circuit, it is also plus VDD. Therefore, only in one type of circuit we are using biasing potential as negative. Then type of load. So for CMOS circuit, type of load is CMOS transistor induced type. Here NMOS transistor diffuse type. Here we do not have any mentioning of load because it is a combination of both the CMOS network and NMOS network. In no situation for a CMOS circuit there is an active current flow. So As because there is no active current, so there is no loading of the circuit. So as such, we do not specify any transistor or any network as the load transistor. Is it clear for CMOS circuit? Is it clear or not, students? Yes?
Yes, sir.
Okay. So for pseudo NMOS circuit, again, load transistor is MOS transistor induced by. So any other parameter? Yes, we can increase discussing the comparison. So maybe further points also. Maybe one of them is connectivity of the the load connectivity or load connection. So for CMOS circuit, what is the load connection? Here, the gate and drain shorted. Here, the gate and source shorted. Here we do not have specific loading, so nothing regarding the load connection. Here, gate grounded. Is it clear about the comparison? Tell me. Is the comparison table clear to all of you?
Yes, sir.
So here, do not forget that this capital N is nothing but the number of inputs. So capital N represents the number of inputs. So it is evident that another very important point we have.
Sir, power efficiency.
Yes, that is the power efficiency. Power efficiency. So for CMOS circuit, it is ideally 100% power efficient. It is ideally 100%. Rest of the circuit, not 100%. It can differ from anything in between. Not 100%. Therefore, we can conclude that for CMOS circuit, there is no active current flow through the circuit. In all the other kind of circuits, there are a certain amount of active current flow through the circuit, and therefore the power efficiency is not 100% for CMOS, NMOS, or pseudo NMOS circuit, which is 100% for CMOS circuit. So one thing very contrast is we may have a higher amount of volume for CMOS circuits because here the number of transistors are almost double. So if you have 10 input signals within a particular Boolean expression, say there are 10 variables, distinct variables. what you find that there will be a requirement of 20 transistors within CMOS circuit, whereas rest of CMOS, NMOS, and pseudo NMOS circuits will be formed by only 11 transistors. So there is a huge difference in terms of size. Almost the CMOS will be almost the double the volume is that of NMOS, PMOS, and pseudo NMOS circuit. But still, it is more power efficient than the other form of circuit. So it is not always so that higher the silicon area, higher will be the power consumption. So that theory somehow gets unverified over here. So that theory doesn't stand over here somehow. For CMOS circuit, even if the volume is larger than the CMOS, NMOS, and pseudo NMOS circuit, it is more power efficient than the other three circuits. Is it clear to me?
Sir, it is clear, but I do have a doubt. Like earlier during our architectural classes, we have mentioned that if there is higher hardware complexity, the power demand of the circuit also increases. But over here, you are saying it is efficient. But does the power demand remain same for all those circuits, or it is higher in CMOS?
No, that is a very general rule that higher the silicon area or higher the hardware overhead of a particular circuit, hardware complexity, higher will be its power consumption. That is a very general theory, and that stands true for most of the kind of circuits which we have in our day-to-day life, most of the kind of devices. But when you compare this transistor level circuitry of whether it is made up of a single transistor like PMOS or NMOS circuit, or it is made of multiple kind of transistor like pseudo NMOS circuit, but we do not have any pull-up network, active pull-up network. Uh, Whereas if we compare these three kinds of circuits with the CMOS circuit, very specifically designed for lowering the power consumption, we find that even though CMOS circuit is a higher volume, higher size circuit, where in terms of your architectural concept, maybe the hardware overhead is more, but still we have less amount of power consumption due to its functional criteria. We have made the alignment of transistors in such pattern that in all circuit operations it will consume no active current from the power supply. Right? And so in today, most of the most of the circuits which are there are CMOS circuits rather than individual CMOS and NMOS. Now, within those CMOS circuits, say every circuit in today's world is any architectural or organizational component of your computer is a CMOS circuit, then again that theory applies that higher the hardware complexity, higher will be its power consumption. Why? Because mind it, just look at the row of power efficiency I have written. I have written ideally 100%. Practically, it will not be 100%. There will be some amount of leakage current flowing through the CMOS circuit also. And those leakage currents will be the reason for leakage power consumption. There will be a power consumption which is named as leakage power consumption. And if you compare the leakage power consumption values of different CMOS circuit, then again that old theory applies that whichever CMOS circuit is having higher number of transistors or higher amount of hardware within it will have a higher tendency of leakage current flowing through it or higher amount of leakage power being drawn by it. Did I make the thing clear or not?
Clear, sir.
Okay. In other than the explanation I gave just now, please wait for few other lecture classes after which we will be moving into a chapter totally dealing with the power consumption of VLSI. And there we'll find that there are different kinds of power conservation, different kinds. Now we are dealing the power consumption which I am mentioning is static power consumption. Is static power consumption, whatever be, whether it is the active current drawn, the power consumption due to the active current drawn by the circuit, which is for the PMOS and NMOS circuits or pseudo NMOS circuit, or whether it's the power consumption due to the leakage current drawn by the circuit. Each of these power consumptions fall into the domain of static power consumption. But there is a very gross power consumption component also felt within VLSI circuits called dynamic power consumption. So all these complexities of how power is consumed, what are the different power equation parameters being to be considered, everything will be dealt in that particular chapter of power consumption within VLSI circuits. So to make your concept 100% clear regarding the power efficiency of these hardware components or transistor level circuits, please wait for that particular chapter. It will be more clearer as you will be garnering more knowledge. Is it clear? But broadly classifying whatever I did mention in your architecture or organization classes, that higher the silicon area or higher the hardware complexity, higher will be power conversion. That is a very broad and generic concept and very much valid concept. But as and when you move into your low power circuit design criteria, because other than time and efficiency, functional efficiency, power efficiency is today in a very important thing to be considered by the VLSI designers in today's world. And most of the circuits they are trying to design the alignment of transistors, they are trying to make the channel length of the transistors, they are trying to decrease. With everything concerned with whatever will be the power consumption. So ultimately, there will be some special cases to be dealt with other than the very generic concept which we have learned and which is valid. Clear, Yoga?
Yes, sir, clear.
Anyone else with any other question? Okay, so this will be up to today's class, and we will be having our next class on Monday, 9 o'clock. Isha, is has told that he will be taking 9 o'clock class. Have you scheduled any class? Isha? Isha is there or not? Yes, Isha or anyone else? Is there any scheduled class at Monday 9 o'clock?
Sir, as per my information, there isn't a scheduled class as of now.
Then just schedule my class at 9 o'clock Monday.
Okay, sir, I will convey the message to the CRs.
You just convey the message to the seer and also you may write it to your other students.
Okay, sir.
Okay, Monday 9 o'clock I will be taking the classes because you all know that there is a GO or the government order being circulated that from Monday we will be having, we will have to attend the office. Also the students will be, I think the offline classes are scheduled to start from 16 November. I don't know whether how it will be, what will be the sanitization system, everything. That I don't know the details administrative process, but maybe it will be from 16 November. But we have to move to our office from 1st November, Monday. So I don't know whether there is any infrastructure. As of far as my knowledge, there is no infrastructure of taking classes from the institute. So I will be covering up my lecture, which is scheduled from 10:50. I will be taking that from 9 o'clock. Is it clear?
Sir.
Yes, sir.
Okay, so the thank you everyone.
Thank you, sir.